Okay, very good afternoon to all the participants in this call. I hope we are all set to go. Uh, and we are privileged to have our honorable speaker as well with us, Dr. Somnath De from IIT Indore. He has already joined the call. Today is the second day of 1 week faculty development program organized by Hooghly Engineering and Technology College, IQAC, in collaboration with HETC Innovation Institutions Innovation Council, that is IIC, and Entrepreneurship Development Cell, EDC. Uh, in this 1 week faculty development program, speakers from different corners of the world, they have consented to take part as resource person. Yesterday, we had two sessions. The first session was conducted by Dr. Saurabh Mollik from the University of Arizona, USA. And in the second technical session, Dr. Shumanto Roy from Sidhu Kanu Birsa University, West Bengal, he deliberated. Today, it is the third session, or in other words, the first session of day 2. And today we have amongst us Dr. Somnath De, Associate Professor, Computer Science and Engineering Department, IIT Indore. Uh, Before we start the lecture today, let me introduce our honorable speaker. He has got a vast experience and he has got varied achievements under his belt. So just to mention a few, let me start this way. Dr. Somnath De is an associate professor currently in the Department of Computer Science and Engineering at the Indian Institute of Technology, Indore. He has previously held the positions of Head of the Department of Computer Science and Engineering and Associate Dean of Administration at IIT Indore. Dr. De received his B.Tech degree in Information Technology from University of Kalyani in the year 2004. He went on to complete his MS and Ph.D. degrees in Information Technology from the School of Information Technology at the IIT Kharagpur in 2008 and 2013 respectively. With over 40 research articles to his name, including papers in international journals, conferences, and book chapters, Dr. De is a distinguished scholar in his field. He has been honored with the Young IT Professional Award Eastern Region by the Computer Society of India. His research interests encompass biometric security, image processing, and pattern recognition. Dr. Somnath De is actively engaged in academic and industrial collaborations for research and development. With more than 7 years of extensive experience, he has served as the Technical Program Committee Chair and member of several prestigious conferences. So, on behalf of the entire HETC family and the teaching fraternity of HETC, I, Dr. Shubham Ganguly, Assistant Professor, Basic Science and Humanities Department, cordially welcome Dr. De to this 1 week faculty development program. And thank you so much for consenting to this FDP. I hope that this session is going to be a very, very learnable session. And definitely it's going to give a lot of insights on the topic. And let me announce the topic as well. Just now I got a brief from Dr. Somnath De. Today, the title of his topic is Mathematical Foundation of Generative Adversarial Network. I repeat, Mathematical Foundation of Generative Adversarial Network. It is the title of his lecture today. Over to Dr. Somnath De. I hope you all will enjoy this session, and it's definitely going to be a great learning session. Over to you, Dr. De.
Thank you, Dr. Shubham, for nicely introducing me. And I would also like to have a privilege to be a part of this FDP program organized by HTC. So without delaying these things, I am going to share my screen. So I request you to kindly give the permission to another Somnath De is there. So in that, because I am going to share my presentation from the laptop, sorry, tablet, so that as it is some kind of mathematical foundation, I have to write something on the screen. Okay. Thank you for giving the permission. First. I think my slide is visible now in presentation mode.
Yes, sir. It's visible.
Okay. So also just before going to start my topic, I will request you to give answer when I ask some questions. Okay, so at least that makes this presentation interactive, because nowadays online lectures are kind of a one-way delivery. In general, I don't get any response from the other side, so that doesn't look good. Okay, so I request all of you. So whether your answer is wrong, right, that's fine. I don't mind these things, but you should try to give the answer of those questions. Okay, so today I'm going to talk about this mathematical foundation of generative adversarial network. So many of you, might not be all, are familiar with deep learning models, different deep learning models. Okay, so on those deep learning families, there is an called GAN model, GAN, that is generative adversarial network. And why I have chosen these topics, because nowadays that generative AI is becoming a kind of a boom, or lot of research is going to be happened. So that's why I have chosen this topic, generative adversarial network, and a lot of applications are there for this generative adversarial network. Uh, but its mathematics is a little bit complex. Sometimes when we read some research paper, we try to avoid that mathematics. We try to get the code from the internet, because nowadays a lot of GitHub codes are available. So we try to incorporate that one and then try to modify that one according to our application and go for those training and testing things. But in this lecture, I will try to describe the mathematics behind that model and idea behind that generative adversarial network model, so that whenever you will go for those codes, without hesitating, you can change. Means if you change something in that code, so what is going to happen, you will be able to understand that thing. So that's why I have chosen this topic. And so today, first, I will give some introduction, then why we'll go for this motivation part, means why we'll go for this GAN model with some applications, and then generative models, because there are multiple means many generative models are available. Okay, so we will see what are the different varieties of generative models are available, and under which category this GAN is going to come. And also I will discuss another two small generative models in my lecture. I will give the brief overview of that, not in details. And then I'll go for this core part, that is generative adversarial network and deep learning, deep convolutional generative adversarial network, that is DC-GAN. And also I will show some implementation, so that basic implementation, which will go for training of 5 epoch or something like that. And we're going to try to look or map our mathematics into that implementation. Okay, so that's our purpose of this implementation. Okay, now what generative model do? So can you identify what it is? Can anyone identify? It's an image. Okay, so I should start with this one. Okay, what is the first image? From this, are you able to distinguish anything? No, it's kind of a black and white dotted images, like random noises. Second images, are you able to guess anything from that image? No. Third image? Are you able to guess something there in the third image?
The shades are quite different, I think.
Shades are quite different. Can you little bit zoom and check anything you are able to identify?
There are some hidden numbers, I guess.
Number. Okay, now something you should be able to see here.
Yeah, some 0, 2, 0. I am able to see 2, 0 in the third one.
On fourth one, that right side top.
Okay.
Sir, it's a 100 rupees.
Actually, it is a
100 rupees.
picture of a currency.
100 rupees note.
It is a picture of a currency.
Currency.
Yeah.
Okay. So now this one more prominent.
Yeah.
Now
Right.
this is
Yes.
like actual.
Now,
Okay. So let's say if I am generating this 100 rupees note and you are going to distinguish whether that note is real or fake. So for these first 5 images, you will be easily able to distinguish that these are the fake images or generated images. But in the sixth image, it's quite actual, means it looks like actual 100 rupees note. If I take a proper printout, it would be it looks like an 100 rupees note. So that means as a generative model, we are going to generate something which will looks real. That's the task of the generative model. But how it is going to generate that one? Because someone should get to know whether it is going to be generated more realistic image or not. Not only for the images, it could be for the text also, it could be for the sound also. Okay, or any data if you want to generate, that could be more realistic. Okay, so initially I have started with some random noises. That means for a generative model, our input will be with some random noise, and from this random noise, I am going to generate this real image. So that's the task of a generative model. Okay. Now coming to this, how do we get to know that what type of images I have to generate? For that, I need some training samples. Let's say if I take a multiple snaps of an 100 rupees note, and I can take the data distribution, that is probability distribution, which is going to be represented by P data X. Okay, so this is the probability distribution of your real images. So that is my training samples. And what is our target? I have to generate some data that is generated by model, and that probability distribution will be same as my training data. Not same, exactly same, almost same. So if it is same, so that means you are Sumit, are you going to say something?
No.
Okay. So here our target is to generate the data whose probability distribution will be similar to my training data. That's the task of my generative model. That means given a training data, we are going to generate new samples from this same distribution. Okay. So are you able to see the right side image or it's lagging? I think you are able to see only left side image or right side image also? Can anyone
Yeah, we are able to see only the left side image.
left images? I have to rejoin. Okay, so I will share. Just when I'm sharing, actually my tab is disconnected. Yes. I have to share it from here again. I think now screen is visible with this.
Yes.
So now are you able to see the right side image also?
Yes, sir.
Okay. So in this part, I will take. So from the training data, I have to generate some new data whose probability distribution will be similar to this P data. Okay, so that's our target for the any generative models, not only for the GAN, that is target for any generative model. Now coming to the application part. So what are the application where we could apply? So we could generate the new images. Let's say if I have, I want to generate some sort of kids images, so which look, you can see that in the left side images, structure is almost same, but skin tone and face eye part is a little bit different. All these are generated images. It may happen that these kids are not exist in the world, but you are able to generate realistic images. And same thing for that right side images. Okay, so these images are generated artificially. Okay, so through the machine learning. So when you are going to generate something that should look real. Okay, so that is one application of generative model. Second application, so that is, if I want to generate some cartoon characters for a particular person, okay, or particular celebrity, we can also use this generative model. And you can see that from the all these images, the right side images are cartoon generated from the actual photograph of that person. Third application is image translation. What do you mean by image translation? Let's say if you have an image of zebras, but on that same background, you want to convert those zebras as a horse. So that could be done also using these generative models. And if you want to change the background, like if you have a summer image photo of a summer season, so if you want to convert it into winter, or if you have an winter season image and you want to convert it into summer season, so that is also possible using these generative models. And in this super resolution image, if you look into this part of the image in the left side where I'm highlighting, so you can see that that is not properly visible. So sometimes if we are going to take the satellite images with high resolution, some part may not be visible, but I want more details on that part. In that case also, we can use these generative models. After using generative models, you can see that this part is clearly highlighted, or same thing for this part. Okay, so more details are available. That type of application used the super resolution generative models. Okay. Now I think you got the idea how means what are the applications of generative models and how we have to generate these things. Now I'm just coming to that different types of generative models. So generative models, first of all, generative model that from a given data, we are going to generate a new sample, which distribution will be similar to my training data. For that, one thing we need, that is the density estimation. Because this is the main problem. Let's say I have given you an image, multiple images of a person. How do you measure the density? And based on that, and that problem is an unsupervised learning problem. So based on that problem, we are going to categorize our generative model into multiple ways, because we can generate this density of the data, probability density of the data, using explicit mode or explicit density estimation, or it could be implicit density estimation. So explicit density estimation, where you are going to give the exact define and solve the you are going to define this probability density. Let's say you have given an image, you have calculated the density, probability density, and you are providing that to the model. And another way to, you just give all the images to the model, it is going to calculate the density, probability density. Okay, so in that case, that type of density estimation is called implicit density estimation. Based on these two types, we are going to categorize our generative models into two part, that is explicit density model based generative model, and another is implicit density based generative model. And in explicit density based generative model, we can use the traceable density, where you are going to calculate the actual density, probability density, and for that fully visible belief networks are used, and under that NAD and MAD and pixel RNN and pixel CNN are those type of generative models. And in some cases, we are going to estimate the density approximately. So for that variational autoencoder or Boltzmann machine are two types of generative model who are going to use this approximate probability density. And implicit density, where we are going to give our entire training set to the model, and it is going to compute the intensity or probably not intensity, probability density. So that type of model are that is the GAN model and the GSN model. Okay. So based on that, actually based on this density estimation, we are going to categorize our generative models. So in fully visible network, what is going to happen, that we are going to apply some chain rule. That means when we are going to compute the probability value of xi position, so we must know, or it should be given the probability of x1 to xi minus 1. So based on that, we are going to compute the probability of xi position. And it is going to maximize the likelihood of the training data. That means you know all these probability, and then you are going to compute the probability of the xith position. Okay, so that is the explicit density estimation, because you already providing these probability density values or probability values of these points, and you are going to compute this one. And this type of probability density estimation used in one model that is called pixel RNN. It generates the image pixel from the starting from the left top corner. That means if I have this probability value or intensity value, or be specific, probability of the intensity value of this pixel, if I know, I can compute the probability of the intensity value of these next two pixels using our chain rule. And as I know all these three pixel values, so after that I can compute the probability of the intensity of these three pixel values. So in this way, if we process, we will be able to compute the probability of the intensity of each pixel for a given image. And that type of model is called pixel RNN. And in this case, you can see that it's very, you can see that probability density is depending on all the previous pixels. That means it's not a sequential model. Sorry, it's a sequential model. You cannot be parallelized. That means it's very slow. That means if you want to generate an 1024 cross 1024 image, so it will take a lot of time. That's the major problem of this pixel RNN model. So little bit improve over that, we are going for the pixel CNN, where we are going to use a convolutional part. When we are going to compute some pixel of a particular position, we are going to create a window around that. And we are going to use the probability of the intensity values of those positions to compute the intensity of my current pixel. So this would be done within the different window or different convolutional filter. So this is here you can see that it could be a little bit faster because here we will be able to parallelize each of these convolution filter. And but still there is a drawback that you have to process all those convolutional filter. It's still low. So these are the major drawbacks of if you go for these pixel RNN, pixel CNN type models because they are very slow. So now what could be the solution to improve that one? So that is called the generative adversarial network. So in that GAN model, we will first get to know what is the idea behind a GAN and what is the objective function of the GAN model, and try to understand each of these components of the objective function. Then we will try to modify our GAN loss function for our practical uses, because in that original GAN function, if we are going to use in our model, there is many problems that also we are going to discuss, and then how we can modify and we can use it for our practical problem. And then we are going to discuss the simple GAN architecture using PyTorch for handwritten digit recognition. And finally, we are going to show that DC GAN architecture. Now coming to this part, generative adversarial network. So as I have shown in that my initial slide, that introduction slide, let's say this is mine, and these are the this is the discriminator which you are going to answer. When I have generated one image, for the first one, you are easily able to identify that's a fake image. Similarly, if I go for the second, third, fourth, fifth, still you will be able to tell that that is not the original image, that's a fake image. But on the sixth image, the discriminator that you are able to say that that is a 100 rupee note. That's a fake image of a 100 rupee note, or you can say that that is original image. Okay. So here our target is to be just a minute. Just hold for a 1 minute. I'm just coming back. Sorry, actually, our JEE counseling is going on. That's why I received some call. I have to take that one. Sorry for that. My slides are still visible, or gone?
Yes,
Yes,
that
it's
is visible.
Okay.
Yes,
So
sir.
here we're talking about this generative model. That means in this generative adversarial network, there are two components. one is that this generator and another is discriminator. That means one generator is going to generate some images and another is discriminator. He is trying to identify whether it's a real or fake. Generators are going to generate new samples and discriminator are trying to distinguish between real and generated data. Okay, so how it is going to get the real data, because when we are talking about a discriminator, so he must have some knowledge of the which is the original data. That's why there would be some original data as your training data set. Okay. Okay. Now let's look into the task of a generator component. Okay. So what would be the input for the generator? So generator input will be a random noise. Random noise means initially I have shown my first image that is a kind of any random numbers will be there in that image. And it is going to generate the synthetic data. And typically it consists of multiple neural network. Okay, so how this generator is made, it has multiple layers of neural networks. And in general, we use some fully connected layer. In some cases, in that advanced model to reduce the computation time, they use partially connected network, not the fully connected network. But in we can consider this generator model as a fully connected convolutional layers. And what would be generator goal? What do you think with respect to a generator? What it is going to, what this generator is going to try? It's going to generate the sample so that even discriminator will not be able to identify whether it's a real or fake images. Means whatever it is going to generate, your discriminator must say that is a fake image. But generator target is to fool the discriminator. That means whatever you are going to generate, your discriminator is going to say this is an original image. That's the target of the generator. Try to understand these 2 points. So generator goal is to fool the discriminator. That means whatever image he is going to generate, that is a synthetic image. He will try to fool the discriminator so that discriminator is going to say that's an original image. That means that time your generator is, you can say that my generator is working perfectly. And its performance will be measured using a loss function, which will be evaluated how well it can fool the discriminator. If you look into the last point, it has been told that thing, same thing. That means I have given a random noise passed to the generator, it give an image. If your discriminator says that this is a real image, that means he can say that, okay, I am performing better. But if discriminator is able to say that this is a generated image, that means your generator is not working perfectly. That's the goal of generator. Now let's look into the discriminator model. So here discriminator is responsible for distinguish or making the decision whether given image is real or it's a fake. It also consists of multiple convolutional neural network layers, which is trained using our original data set. Because until or unless discriminator doesn't know which one is a real one and which one is a fake one, he will not be able to learn that thing. And what is the discriminator target? Discriminator target will be if generator gives an image, he will be able correctly able to say that that is a fake image.
এইগুলোকে সব বিভিন্ন জায়গায় রাখতে হবে তোমাকে।
Am I audible? There is some.
Yes, sir, you're audible, sir. Sorry for the problem.
Okay, so when I pass a or real image, your discriminator will be able to say that is the real image. That is the target, or that is the goal of your discriminator. Then how do you measure the performance of this discriminator network? That means how correctly he is able to distinguish the real images as a real and generated images from the generator is a fake image. So if it is able to correctly classify these two things, that means your discriminator is going to work perfectly. So this is the two goal, one for the generator and another for the discriminator. Based on this, our objective function is going to be defined. But before going to discuss the objective function, you can think this problem is a min-max game. Let's say if I take a real example of a wrestling, so there are two persons who are going to hit each other. Let's say for the person A, I want to measure his profit or performance, how many times he is able to hit the second person B or second wrestler. In this way, I can measure the performance of my wrestler A. On the other hand, if I want to measure the performance of wrestler B, how many times he is able to block the hitting of first wrestler. Okay, so if I use that performance metric to measure the performance of wrestler B, that is also the correct way. That means one is going to maximize, that means how many number of times wrestler A is going to hit the second wrestler. In case of wrestler B, how many numbers of hit he is able to block, means that means he is going to minimize the total number of hits. Okay, so in that way, if you think, that means one is going to maximize and another is going to minimize. So in this case also, we can think with that perspective, that generator is going to make generator is going to minimize and discriminator is going to maximize his profit, that he is able to classify real object as a real and fake object as a fake. And your generator is try to fool the discriminator. That means he is going to pass those generated images to the discriminator, and it will try to say, it will try to reduce those numbers. Number means your discriminator should able to less number of images, generated images should be classified as a fake. So in that way, we can define our generator is an minimizing player, and the discriminator is an maximizing player. Okay, so based on this concept, we can define our architecture like this. So in our architecture, you can see that these are the random images are given to this generator. The generated samples are represented as GZ, which would be passed to the discriminator. And in case of discriminator, he is going to take the real samples. Here I have taken the fingerprint images. So here also generator is going to generate some fingerprint images. So now discriminator task is to distinguish whether the generated images is the image he received, that is from the real sample, or it's a generated fingerprint. Okay, so based on that, we can compute the loss, and we can propagate this loss to either discriminator or generator based on the training which we are going to update. Now, it's here I have given more elaborative diagram. So discriminator model, there are two models. You can see that generator model and discriminator model. So when we are able to get some values that is real or fake, so those values, based on those values, so we can compute a loss function. If we are going to train the discriminator, we are going to pass that loss value or updated value to this discriminator model. If we are going to train the generator model, that time we are going to pass this loss value to this generator. Okay, but here you have to think in this way, that how we are going to perform this training for the discriminator and for as well as for the generator. Training are not going to happen parallel. Training would be sequential. That means first your discriminator is going to train. After that, your generator is going to train. And this process will repeat in every steps. Like when we are going to train the discriminator, here you can see I have locked the generator. That means that time generator is not going to train. Whatever images he has generated, that would be passed to this discriminator, as well as all the training sample will be passed to the discriminator. And from those data, it is going to take how many falsely he is able to, how many correctly he says real images as a real, fake images as a fake, and based on those values, we are going to compute the loss value, and that loss is going to propagate to the discriminator. That means when I am going to train the discriminator, your generator must be locked. Okay, that means he is not going to generate any, or he is not going to update his weights. Okay, he is going to generate with the existing weight. Now, if you look into the discriminator model, generator model, your discriminator is once trained. That means he is able to classify original image and fake image correctly. So now you use those discriminator model with those weights, and whatever image you are going to generate using this generator, that is going to pass to the discriminator. That time we don't need any training samples for the discriminator. So these generated samples, how many generated samples are classified as a real and how many generated images are classified as a fake. Based on that, you can compute the loss value, and that you can propagate or back propagate to this generator model. And it is going to update accordingly, and again it is going to generate the samples. Okay, this this is the training process of an GAN model. That means generator is going to generate once and discriminate. So when generator is going to train, that time you have to lock the discriminator. When you are going to train discriminator, you have to lock the generator training. Now already we get to know what is the goal of this generator as well as the discriminator, which I have already explained. Now coming to this mathematics. So if you look into this Ian Godfellow's paper, who is the developer or proposer of this model, so he has given this type of equation. It looks very tricky type of equation. So here you can see that we have used mean, and below that we have used G. Here max, below D, V, D, G. Here E, X, P data X, log dx, Ez, Pz. Lot of equations are used here. Now let's understand each of these terminologies. So what is the objective function? So objective function should be for the generator as well as the discriminator. So that is represented by D. D represent the discriminator and G represent the generator. And V is the objective function. Now, with respect to generator, we are going to minimize this entire function, and max D means with respect to discriminator, we are going to maximize this function value, because we have seen that when we perform the training, or we are going to update the weights of generator or discriminator, either we are going to do it for generator or we are going to do it for the discriminator, not together. So that means one is going to generate or maximize, one is going to discriminator is going to maximize this function value and generator is going to minimize this value. So I think left part of this equal sign is clear. Left part of this equal sign is clear. Okay. Okay. Now coming to the right side part. So I request participants to mute their mic if you are not answering any questions. So please mute your mic. Okay. So now here I am talking about this dx function. This is the discriminator function. This discriminator is going to take an input x. X is your training data. That means if I am using 10 images, x represent one of that image. So x represent the vector which contains all these 10 images. Let's say if I represent xi, x1, x2, x3, x4 like that, that means each is going to represent one of that image. If I pass that image into this function, that discriminator function, it is going to give you some probability value. Probability value of that, let's say it gives an 0.8. And based on that value, you are going to take the decision whether your discriminator is going to say it's real image or it's a fake image. So here you can, that means here we are going to get some probability value. And this E double line represent the estimate of your training data. That means if I pass a single image, you are going to get one probability value and you are going to take the log. If you are going to pass all these 10 images, so you will get 10 probability value and corresponding log value. And if you take the average, that is going to represent this estimate. Normally we use estimate when we use this continuous variable. Otherwise, it can be replaced as a simple mean of this one, this value, this log value. And similarly, if you just look into the right side, so in this right side, here you can see that I am passing GZ. What is the Z? Z is the random noise which is passed to the model G, that is generator. That means G is going to give you an output as an image, which is a synthetic image. That means from a random noise, your generator is going to generate an image which is passed to my discriminator, this D. Again, it is going to give you the probability value, that is either between 0 to 1. So if I got that probability value, here I am going to subtract this value from the 1. Why I am going to subtract it? I am going to explain this one. And I am going to take the log value. And this E represent the same thing like estimate. If I am using discrete variable, so this could be represented as a mean of all those values or all the input I have given. Okay. Now, if you remember, the probable goal of discriminator is to classify real images as a real, fake images as fake. Now, if I pass a real image here, that means I am passing X. In that case, your discriminator must give value probability near to 1. And the log of 1 is equals to 0. Okay. And in that case, this part is not come into the picture. Now, if you pass a generated sample, that time this part will not come into the picture. So GZ is the generated sample. Let's say that I am representing as a X bar. And with respect to generator, okay, so first talk about the discriminator. With respect to discriminator, what should be the output here? It should tell this is as a fake image. That means probability value will be closer to 0. Then only it is going to be say that is the fake images. And if it's 0, that means 1 minus 0 will become 1, and log of that will be again 0. That means if your discriminator is able to correctly classify real images as real and synthetic images as fake, so overall value will be for this function will be 0. Now, if your discriminator is not working properly, that means if it gives some value where this is coming 0 or this value is coming near to 1, so that time overall value is going to be minus infinity. That means our target for this discriminator is to get 0 value, but if it's not working properly, you are going to lead towards the minus infinity. That means our target or objective function, this objective function with respect to discriminator must be maximized from minus infinity to 0. That's why here it's maximizing with respect to D. Now coming with respect to G. Okay, let's say if I am passing the G, what is the target of G? G's target is to fool the discriminator. So that time this part is not going to come into the picture. Okay, so that I can discuss on this part. Okay, so first part is not going to come into the picture. Here I have replaced my estimate with the average or mean because I'm going to compute for the m number of discrete samples. Now, if this is the generated image, what your generator would expect from this discriminator? What would be the output? Will it be high probability value or low probability value? So here your discriminator is this generator would expect that your discriminator will give high value near to 1 probability. Then only your generator is going to work perfectly because that time you are passing a generated sample, and your discriminator is going to give value or probability closer to 1. That means your generator is able to fool this one. Now, if it becomes 1, so this value becomes 0 and log of 0 would be approximately minus infinity. Okay, now if your generator is not able to fool this discriminator, he is going to give some probability value closer to 0. And in that case, this value 1 minus 0 will be 1 and log of that would be 0. That means our generator target is to get the objective function value minus infinity from the value 0. Okay, that's why it's a minimization function with respect to the generator. If you have any question, please let me know. There is, I can continue. So here it is going to minimize. So what I explained that has been given in this part that with respect to discriminator. So when we are going to update that value, how much updation is required? We have to take the gradient of this function. So that much updation is required. And that would be, as it is an maximize function, we have to use the gradient ascent function. Okay. Gradient means we are going to take the derivative with respect to this discriminator part. And if we talk about generator, generator is going to minimize this function. So we have to use the gradient descent function to update the weight of your generator, which is represented in this part, and where this probability would be the predict badly on the fake images. Means if you are passing the fake images and your discriminator is going to say that is a real image, that means it is going to give you the probability closer to 1, and here you are going to get the negative values. Okay, and here is that algorithm format of this training algorithm. Training part. So you can see that there are k number of steps we are going to follow for training, and each of these iteration we are going to update first the discriminator. After training of this discriminator, we are going to apply the training of the generator. An initial input of your model will be m random number or random noise and m number of real samples. When you are going to train the discriminator, both of these are going to use here. But when you are going to train the generator, so you are going to use only the random noise, not these actual samples. Okay, so this is the algorithmic format of your GAN model. Now, when we'll say that when we'll stop this algorithm, so when your GAN model is converged when it reaches to Nash equilibrium, means if it's getting zero sum, okay, for your min max gain, that is referred as a Nash equilibrium. Or in other way, we can say that if I am sending an image to the discriminator, it is not able to tell whether it's real or fake correctly, means its probability is closer to 0.5. So then you can say that my discriminator, my generator model is properly trained. But main problem of this GAN model is that when we are going to perform this training, one function is used as a gradient ascent and another is a gradient descent. So these two functions oscillates very frequently, and due to that reason, it could happen that your discriminator is not able to update the loss properly. So due to that oscillation. And sometimes another problem happens, that is mode collapse, when generator are producing just one types of sample. Let's say I want to generate the sample of handwritten character 0 to 9, but it is always going to produce a particular number like 1. So then that type of problem can occur due to this mode collapse. So that type of problem is referred as a mode collapse. And another problem is if your gradient is too strong, means whatever generator is going to generate, it is always going to say that is as a fake images. And whatever real images you are going to give to your discriminator, it is going to say that is as a real image. It's a too strong discriminator. That time also your model is not going to learn properly. Means your generator is not going to learn properly due to this vanishing gradient for the generator, which are going to use the gradient descent problem. And we have to overcome this problem for our real applications. But discriminator is too weak. It's a very rare problem because there won't be, we not, in general, we don't consider that type of discriminator, which is not able to say the simple thing. Let's say if I send those dotted images and the actual images, it is not able to distinguish between that. So that type of discriminator normally we don't use. So that is a very rare problem. But major problem due to this third point. Okay, so due to the vanishing gradient, it may happen that it is going to oscillate high. So what we are going to do, instead of gradient descent function in the generator, we are going to use the gradient ascent function. So here we are just remove this minus symbol, and this is going to be used as a discriminator, d of zz. And this gradient ascent function is also going to be used for your gain. And if I look into the loss function, so if I going to implement this loss function, these values, we can easily use that binary cross entropy function. So binary cross entropy function is represented by this y label, and y hat is the what is the output of that. Y is the original label, and y hat is the predicted label for the ith sample. And if I multiply with this or log likelihood or binary cross entropy, so we can easily represent this above function, that gradient ascent function for the discriminator, with this one. For example, if you passing the real images means this label is 1. And also with respect to discriminator, I want that should give you the 1. And if you just multiply this one, so here you are going to get the negative value. And in this case also, it's if you are going to give the fake images, so your y value is 0, so this part would be neglected. Now, if it gives y bar as some positive value or means some negative value, that time it is going to be positive. But your target is to minimize this. Okay. And same thing for the this gradient loss function for the generator, where we are going to replace this one with this. When we are going to use the gradient descent one, so I can use this cross entropy function or BCE loss, binary cross entropy loss, with this function. Okay, so this part is for the discriminator, so it is not going to come into the picture. So here you can see that if I flip this sign, this becomes the same. But flipping sign on that objective function is not a good practice. So what we are going to do, we are going to change the label of the real images or flip the label of the real images to the 1. And this becomes our gradient ascent function. The left part of this loss function, binary cross entropy function, becomes the same as gradient function, which normally you are going to use for the practical usage. In this case, now both of your update function becomes a gradient ascent function. So we are able to solve that oscillation part. That means one part is going to up and another part is going to down. So instead of that, both updates are going to be based on this gradient ascent part. Okay, so here we are going to change the label and we are going to use this binary cross entropy. Okay, so if you have any question, you can ask. So otherwise, I will go for the simple GAN implementation part. So I think no questions. Yes, please tell me.
Dear participants, if you have any question, please feel free to ask your question in the chat box, or you may unmute your microphone and ask questions.
So, are you able to see this? Are you able to see this notebook?
Yes, sir.
So as I told that we have to design two network. One is generator and one is discriminator. So here we are going to use the PyTorch, and first of all, I am going to thank this author who has, from where I have taken this code. Okay, so from this Docker, that reference is also given. And the first part, what are the basic libraries required for this implementation of this deep learning model? So I have imported those, that Torch library, and from that Torch we have imported the NN, imported as NN, and math library, matplotlib, torch vision. Okay, so these matplot, torch vision are required to visualize our output. Okay, and torch, here we have used some manual seed because we are going to generate some random numbers. So here we are use manual seed for that. And based on the devices, whether we are going to implement using CUDA or GPU or in CPU, we can specify that torch device, that is either it's CUDA or it's on CPU based. And we are going to create this transform, that normalize function. Okay, so all data is going to be normalized using this transform function. Okay. And training set, we are going to use that MNIST data set. For that, we are going to download to, and we are directly going to download from this benchmark data drive. Okay, so if I make this comment, it is going to download all the data from this place. And after that, because here I already ran, because if I run here, so it may take time. So that's why I already prepared this one earlier. So I have used batch size of 32. And this basic thing, train loader and all these things, I have made the sample of those data loader part. This is the common thing what we have to do whenever you are going to perform any training, any kind of training for the deep learning model. So here we are doing that one. Okay, so now how your actual sample look like. So these are the handwritten character. Here are the some samples is given. So initial 16 samples are printed here. These are the original images which are in our data set. Okay. So now in this part, you can see that first we are going to define our discriminator. Okay, so discriminator, we are going to use that sequential model, and we are going to use that linear convolutional layer, ReLU as an activation function, and we are also using some dropout of this data. So your image, each of these images are of size 28 cross 28. So that's why my input to this layer would be 28 cross 20, that is 784. And that first layer is going to give you the output of 1024. And we are in the next layer, we are going to give that input 1024 dimensional, and it's becoming, it's going to reduce. And finally, we are going to get a single output, and we are going to apply the sigmoid function to take the decision. This sigmoid function is going to give you that probability value, and based on that, we are going to take the decision whether it's a real image or fake image. That's my that should be my output of my discriminator. So this is the discriminator model for that, and we are going to load this discriminator into that GPU. Okay, so this part is going to load this discriminator. So here discriminator is going to load. If I call this now generator model, generator is also consists of 4 linear convolutional layer. And here our input is random noise of 100 dimension. That means I have taken 100 random values, and that is going to map as a 256, then 256 to 512. And finally, the target of my generator is to generate 28 cross 28 image. So that output means 784. So here we are going to get that 784 dimension. And after that, we are going to pass through this 10H function. And this is the basic thing for the generator when how we are going to load this one. And this generator is going to output should be viewed as a 28 cross 28 as an image. Okay. Now, as I told that I can replace those cross gradient descent function and gradient ascent function with the BCE loss, that binary cross entropy loss. So here we have used the loss function as a BCE loss. And my learning rate is 0.001 and I have run it for 10 epochs. And also we have to define the optimizer. Here we have used the Adam optimizer for both discriminator as well as for the generator, because these two are two different separate models. Now for the each epoch, you can see that first we are going to train the discriminator. So when we are going to train the discriminator, we are passing the real samples from the MNST level we keep as it is, and your real sample are labeled as 1. And latent sample means generated samples are labeled as, you can see that 0. Okay, so here these 2 points you must notice that when I'm going to train the discriminator, I'm not going to change the label of the data. So we are keeping real data label as 1 and generated data or synthetic data as label 0. And we are going to concatenate all these samples using this catenation function. And after that, we are going to pass all these values to the discriminator function. And we are going to compute the loss, and finally, that loss will be back propagated and your generator is going to train in this part. Now, if you come to the section of the generator part, so earlier part is for the discriminator. Now for the generator, so we have input of only the latent sample, that is all random noises. And here you can see that we are going to change the label of this as a discriminator label. Means here we are going to use this generator as a real sample. So that means here my samples would be labeled as a 1. Here we are going to flip the label. So in this part you can see that we are passing the real sample labels. Means though we are using our data for the generated sample, but we are going to use that label as a real sample. So that you can see here in this function that we are going to change the label for the fake images. Okay, so that we are going to do in this step. Okay, and finally we are going to train this one, and after each epoch we are going to plot this one. Now here you can see that after 10 epoch it is going to generate some sample like this. Here if I go for more number of epochs, you will be able to generate more accurate symbols. Okay, this is very simple implementation, and you can change these loss functions, and also you can change these activation functions. Okay, and you can use different dropout also to this experiment on this. Okay. Now coming to the second part of this. So here I am going to show you the how we are going to implement DCGAN architecture. It's a simple way, but you can see that for the generator, when it's going to take the random noise. Now it is going to reshape into 4x4. So different convolutional layer with the strides, we are going to finally generate an image of 64 cross 64 with the 3 channel. Okay, that means this is the output of our generator. And when we are going to talk about the discriminator, so we are going to pass this image into the discriminator, which was generated by my generator. So that is going to pass in the discriminator, and finally we have to convert or we have to apply different convolutional layer and make it 4 cross 4 cross 256. So it should be the input of my discriminant means based on this value, it is going to give you the output with some probability value, and based on those probability value, we are going to discuss. We are going to decide whether it's a real image or fake image. Okay. So here in this case, DCGAN we have used 64 cross 64 images, and okay. So here I have used in this figure I have used 512, but actually that would be a 100 from the random number this. Okay, so because in that part is showing from this. This is the architecture of this DCGAN. Okay, so now if you have any question, you can ask. Otherwise, I'm going to stop here.
Thank you so much, Dr. Dey, for this wonderful presentation. Now I would request our dear participants to drop their questions in the chat box, or they can also unmute their microphone and ask questions. I guess definitely this kind of an engaging session. It was not just a one-sided lecture, as Dr. Dey promised at the initial part of his deliberation, that it's going to be a both-way interaction, and definitely it has been a very, very engaging session. Not only a lecture backed by a PowerPoint presentation, but workouts as well as engagements with the participants. Thank you for such a kind of engrossing as well as all-encompassing session. Uh, Definitely. Let me see whether we have any question. Uh, if you have any question, please feel free to ask your question. You can unmute your microphone and ask question.
Good afternoon, Dr. Dey. I am
Yes.
Dr. Bishwajit Haldar. I am Dr. Bishwajit Haldar from HBC. Actually, two questions from my side. Actually,
Yes, please.
one is whenever what you have started, that we have seen that the currency notes or the genuine and fakes.
Yes.
Actually, what's happening in the currency notes, whenever we are going to the check it out, that is not only the image to image checkup, because there is a lots of features have been there. Suppose that there is a number. Number cannot be generated through this whatever the module have been.
Yes, number could be generated.
Saying.
Number could be generated.
Yes, every currency notes have the unique numbers, right? Not only that, there is lots of the features have been there. So originally the currency notes, check, these types of the security documents, specific features have been there. That is, each and every individual documents have the signifying features.
Okay.
So I think that is the image to image.
I got your point. Now tell me, represent this example in other way. Let's say your discriminator is going to identify that this image is generated image or it's a photo taken of a real currency.
Yes. I am asking that image to image.
Yes.
So another question, sir, that from the basically for the checking for the discrimination side.
Yes.
The question is raised normally whenever you check it or compare between these two images, that which features specifically differ from the original one. So that type of the process is normally come.
Okay.
So can it possible that from this model that which features is specified, that features is discriminate between these two images? There's lots of the features have been there.
Yes, lots of the feature, because when you do the feature mapping, okay, normally what we do in case of to visualize that thing, that which part of that feature is going to make the discrimination between this real and fake, we generate a heat map of that two images. Means if I pass a real image, what is the heat map of that feature? and what is the heat map of a fake images. Okay, so based on that, we can identify that position, that in this position some new thing are there. And another point I just wanted to highlight, as I told, that is there are two types of model. One is explicit, another is implicit. This is
Yes, yes,
implicit.
yes, yes.
So where
Okay.
all these features are internally calculated, here there is no manual intervention. But if we want to look or visualize, that can be possible based on if you generate the heat map of the features, I mean at the final layer. Okay.
Okay. Okay.
Based
Okay.
on that,
Okay.
you can easily distinguish that which part has given you the discrimination.
Now, where is the heat? Where is the position? Is that specified? That,
Just
that actually
before the
the
last
image is
layer, before
specified.
the last layer, before the
Yes,
last
yes.
layer, you have to add that another layer for visualizing that feature map. Normally,
Okay.
we generally do that to analysis of those results. Means why I'm not getting good results. Sometimes it happens. No, I have applied one model, everything is looking correct. What goes wrong? I'm not getting the correct result. That time we have to analyze. That time we have to take help of that kind of method.
Okay. Okay. Thank you, sir. This is a very useful for us and very nice for presentations. Thank you very much.
Thank you.
So mathematical foundation on generative adversarial network. On this topic, Dr. Day has extensively uh, deliberated, and I guess the participants have been benefited as well as enlightened. Any more questions? Do we have any further question? If you have any query, any confusion, please feel free to write in the chat box. Otherwise, we would like to conclude this session. Well, I guess there are no more questions. I think all the questions and confusions have been properly addressed, and
I think
they're
so. I hope so.
extremely,
I hope so.
yeah,
You will face
yeah.
any problem during the implementation of this.
Yeah, definitely. But if you find any, this is for the participants. If you have any further questions, like after the session is over, you may contact Dr. Somnath Dey. You'd find his email ID on the concerned website of IIT Indore. So get in touch and ask your questions if any. Meanwhile, thank you so much, Dr. Dey, for this beautiful presentation. And earlier also, you visited our college in person,
Yes.
and took part in a seminar as a resource person. That was also a very, very wonderful experience, and we look forward to this kind of sessions in future as well. I hope that again you'd come to our campus in person.
Possibly, if
And
possible, it would be good to be offline.
yeah,
Then
in person, yeah, in
in
person
person is
is
quick.
always better, but at the same time this online mode also gives us several other opportunities, like having
Yes.
people from different parts of
Different
the country.
places. Yes, that's good.
This is also another advantage, but definitely offline gives us that human touch. So
Yes.
thank you. And thank you to all the participants, my fellow faculty members, my technical team, for their wonderful support. uh, Thank you so much. So here we end this session. Please fill out the feedback form
Thank you. So
by
now I'm
5
leaving
o'clock.
now. Okay, I'm leaving
Yeah,
now.
yeah,
Okay.
yeah. Thank you.